Morning, everyone. We'll get started in 30 seconds. Just settle down if you've not already. Okay. So good morning, and here we are, end of week 4, the eighth lecture in this module, and a significant day because later today, I think towards the end of the afternoon, the coursework will be released, and the clock will start ticking. You'll have 2 weeks to turn back the answers. The coursework has 2 questions, which sum to 25 marks total, which, when you're up to speed, so it's modelled on an exam question, when you're up to speed after lots of practice and revision towards the end of the semester and over Christmas and before the exam, those 25 marks should take you, and generally would take you, 30 minutes in an exam. The idea is that you've obviously got a lot longer than 30 minutes in the next 2 weeks to put into this, but the chance is to use that as a motivation and an opportunity to go back and revise and practice, particularly the questions, the topics that we've just covered in the last couple of weeks. Like I said on Tuesday in the drop-in session, if you all get 100% in the coursework, then we've done our job well. There's no problem with you all getting 100%. That is possible. It is a maths type coursework, and if you follow the guidelines and you write clearly and you make sure that you put the units, you use a sensible amount of precision through your answers, etc., then it's very likely that you're going to get a good mark. Please ask us questions through the forum if you have any about the coursework. Please make time to do that. One of the reasons that we are not going to run these in these lectures in week 6 is so that, in theory, you have a bit extra time to look at your coursework. So please, I would recommend that next week you have a first look at the coursework, or straight away you identify issues that you might have or things that aren't clear, and you give enough time to yourself to get that straight and to have a go before you have to submit it. You don't want to leave it to the last minute. Obviously, we're there to help. If anyone asks for the answer to the question on the forum, we're not going to give it to you. But if you are slightly lateral in your thinking and ask for the answer to a very similar question, then we're very happy to give it to you. So absolutely make the most of that. That doesn't mean copy-paste the question and change one number, which someone tried last year. Okay. Right, so today, that should say week 4, we are going into the last topic of part 1, and this is, I think, it's chapter 3 of the book, chapter 3 of the Frank White book, which starts to look at integral analysis, which is really the cornerstone of the analysis you're doing this year and most of Fluid Mechanics 1 next year. Reminder, you've got a tutorial tomorrow at the wonderful time of 5 p.m. But nevertheless, they will be there waiting for you, the GTAs, in Reynolds Building at 5 p.m. tomorrow in the groups that are indicated on Blackboard. Shortly after the tutorial session, we'll issue the paper solutions, and this time, hopefully, we're going to lecture capture podcast the tutorial sessions as well. And it's not 100% guaranteed it's going to work, but that's the plan. So if there's something you didn't understand, you can you have the chance to replay that and maybe understand it a second time. Okay. So this morning we're going to start off by expanding a little bit on the different methods of fluid mechanics. Some of the ones that we introduced right at the beginning, basically analytical, CFD, experimental. We're going to talk much more about control volumes, what they are, how you define them, what do they imply, and what are the questions that they give rise to. And then we're going to discuss conservation equations. And at this point, I'm predicting you're going to be overwhelmed with loads and loads of equations. And I will then reassure you that actually right now, this year, you don't need to worry too much about all the equations. And I'll give you simpler forms, which you're going to be using in the next few weeks. But nevertheless, one of our beliefs is that when you're learning this, particularly this domain, it's really important that you see the context where the equations are coming from. It's much better to give you the full form of the equations now and tell you that we're simplifying them than make up the fact that that you can solve everything with simple equations now and then change the rules in a couple of years and say, actually, you need these complex equations. So bear with me if you start to haze over with the sight of lines and lines of equations, because by the end of it, there's only 2 or 3 lines and things you actually need to remember. And as somebody asked right at the beginning this morning, the equations will be given to you in the exam. You'll be given a crib sheet, a data sheet that has equations and key data. You'll have a look at what you're given well in advance of the exam. And it's not a memory game, it's testing of understanding. Okay, so here we are. Is there any questions up till now about what we're going to be covering? No, I can't see any. Okay, so this is, I think, something that we looked at before. Our 3 approaches to fluid mechanics: control volume or integral analysis, differential or small-scale analysis, and experimental or dimensional analysis. And I'm going to hopefully convince you by the end of today that the first 2 are actually quite similar. They at least have the same roots. One is a more approximate approach to consider large scales. And the second is basically CFD, computational fluid dynamics, which the lovely picture at the middle bottom is showing. The difference being that we're going to go over today, the integral analysis in its first sense is when you apply a control volume to be a very large scale object that has multiple things going on. And a differential analysis is a very small control volume. If you look closely at the diagram at the bottom, you see lots of squares on the surface of the blades of the compressor, and each one of those is essentially a control volume. The concept of a control volume is that you're defining an area that you're going to look at and an area that you're not. And that is defined by these terms, a system and a boundary. A system is essentially usually denoted a continuum of fluid or of a material to which we can apply certain conservation rules, certain physics, approximations. And generally, and what we're going to be looking at here is the conservation rules that we're looking at are mass, momentum, and energy. These are the 3 cornerstones of continuum mechanics. You define a space, you say within that space, matter cannot be created or destroyed, mass has to be conserved, momentum has to be conserved, that's actually Newton's second law, and energy has to be conserved as well. And if we use those frameworks to come up with mathematical expressions that reinforce those statements. So the fluid system is subject to these conservation rules. The boundary is a very interesting and very important thing and often overlooked because it looks like it's just the edge, the thin line. The boundary is really important because it demarcates where you stop your analysis. And that's important because it means that you're making a decision implicit in choosing a boundary between what you want to look at and what you don't want to look at. And what you don't want to look at is everything else, the surroundings. And if you're overambitious and you include too much of the surroundings in your system, it's going to make it complicated. If you're overly simplistic and you include too little of the surroundings in your system, then perhaps you're going to get the wrong answer. So it's a decision that requires experience and consideration, because not only does that determine what analysis you need to perform, but it also determines how do you represent the boundaries. And we'll have a look at some examples of that later. If you're using a high detailed approach, almost by definition, it's going to be expensive, right? It's going to take a lot of computational effort. If it takes a lot of computational effort, it's probably going to be a small region, right? So if it's a small region, that means that it's likely to have boundaries in an area that is also important, because you zoomed in right to the area of importance. And if you're using a high detail method, then you're likely to need to have good approximations of those boundaries. And I'll show you some examples of that later. Okay, so this first one, the control volume approach, is essentially a very convenient and flexible method. And you can apply it to whichever system that you want to make an approximation and analysis on. In this example, we've taken the entire jet engine and said everything in that jet engine we're going to subject to control analysis. We're going to have air going in and air going out. Something happens in the middle. And we represent what's happening in the middle, not by looking at the details of the structure and the temperature and the pressure and the velocity at every stage of the jet engine, but by approximating it as a system change. We effectively have various states in time, or sometimes in space, that are generalizing what's going on in that area. The air goes in at point 1, and the air goes out at point 2. What happens in between? That's the question. That's what we have to apply our integral analysis to understand. In order to answer that question, we need to know what physics is going on, and we need to know what quantities are at the beginning. So it's very, very often based on averaged quantities. The whole point of an integral analysis is that it's fast and it's efficient. And often, like we talked about a few weeks ago, you can approximate something which is much higher dimensions, 3D and time, into something which is just one-dimensional. You can think of this as a process, a line starting on the left, going all the way through the control volume and coming out on the other side. As it goes through that control volume, something happens to it. The temperature increases, the velocity increases, the pressure changes. But because we've defined this as a control volume, this is our system, and this is then subject to the conservation rules. So if the temperature increases, something else has to give. If the velocity increases, something has to change. If the mass increases at one point, then it means that something has to compensate that later. And this is the ethos, the logic of the control volume approach. In contrast, and often in tandem, we use dimensional analysis, or you can think of that as experimental analysis, but it doesn't need to be with an actual physical experiment. You can do it with a CFD as well, to explore the sensitivity of the system. And when you have something as complicated as fluid dynamics, there's a lot going on. Velocity is changing, pressure is changing, temperature is changing, surface tension changing, buoyancy forces, turbulence, drag. You need various different non-dimensional numbers to help you simplify a system. So far, we've talked about Reynolds number. Reynolds number being, anyone remember the ratio of, yes? Yep, very good. And Mach number? Anyone remember what Mach number is? Yep. The ratio of the local velocity to the speed of sound of velocity of the fluid at that point. Others that you haven't seen, aspect ratio is just denoting a geometric representation, drag, CD, representing the non-dimensionalization of a force, D, divided by its dynamic pressure, and the Froude number, which is the ratio of an inertial force to a buoyancy force. And there's, actually, if you go to Wikipedia, the link there, you can see probably about 20 odd or more dimensional numbers that are used in mechanics. And they're important because when you use dimensional numbers in conjunction with system analysis, they set out the rules. They say, Reynolds number is, it's okay to use the Bernoulli's equation if the Reynolds number is this. It's okay to use the Euler equation in fluid mechanics if the Mach number is this. It's okay to use a mass conservation if you want to get a drag range in this. And so using system level analysis, you need the rules and the guidelines within which to operate, and they're very often defined by these numbers. And there's a lot more on dimensional analysis in next year's module. And that brings us to CFD, which, like I've said before, is my area of work. And this is essentially the same as an integral analysis. It's exactly the same approach. You define a square, you define the rules that go on in that square, and you define the system of approximating what's happening at the edges of the square. But the difference is, instead of having one for a system, you have many, often millions, sometimes billions. And the idea is then that you can discern, resolve, a much, much higher level of detail than you can if you just have one. You can think of it like pixels of an image resolution. If you want a high resolution, you need a high number of control volumes. On the flip side, CFD is very powerful because it gives you a detailed, almost virtual insight into what's going on. But because of that, you have to pay a higher price in cost. Cost of the computer, cost of your time, cost of the complexity. But it can be, and is, a very useful metric, a very useful tool. And you're going to learn more about this in your modeling simulation modules. You may already have started, but you're definitely looking at this next year and beyond. And this is a concept that goes back to a thought experiment from Richardson, who's one of our original fluid mechanics guys and led to a lot of work on meteorology. And he, obviously in the absence of computers, the idea of integral analysis could only be taken so far. So in the early days, integral analysis was generally applied where the windows or the control volumes were pretty big. But this chap could see the opportunity, and he could see that if you did have a means of doing a lot of calculations quickly, you could get a much higher resolution, more detailed prediction. And way before the computers were in use, he proposed this forecasting factory where you basically had a whole room or whole system of humans. You can just kind of see them in the corner here, drawn in this visualization of his idea. Every one of the squares that's red and white, behind it has a room of somebody doing some maths, working out the conservation of mass, the conservation of momentum, taking information from the room next door, which are the boundaries, and writing on the wall the updated pressure, the updated temperature, the updated velocity. And this concept that was introduced was, if you like, the first idea of doing a weather forecast using differential analysis. And this is ultimately the concept behind computational fluid dynamics. You don't have a human doing the calculations, getting the numbers from next door and passing them to the following room. You have a computer doing it instead. And I guess, unsurprisingly, you will be aware that computers have absolutely revolutionized engineering. And The example here comes from already something which is 10, 15 years old. A study of the impact of CFD on the aerospace industry. And you can see in the top figure the cycle of an aerospace design, going from conceptual design, preliminary design, wind tunnel validation, preliminary design iteration, confirmation, and flight test. You know, took many, many years. It wasn't uncommon for an aircraft development to take 15, 20 years to get from concept to flight test, which is just absolutely a huge amount of time and effort and money, if you think of all the tests and the investigations that go on. And CFD was able to drastically reduce that by including more virtual tests. And actually that is continuously pushed down. And you can see in the bottom figure really how much was the impact on the A350, which first flew around 8 years ago. And that's continuing. It's a continuing trend. The digitalization of engineering increasingly reduces the cost and the time from concept to production. Okay, so this is one of the first concepts we're looking at today, Eulerian versus Lagrangian methods. And this is something that is only briefly referred to in the textbook, and it's something that you will come back to, and you will, depending on how far you go in the modeling and simulation strand of your degree, you will actually maybe use the two different methods together. And they're basically the theories proposed by two mathematicians to describe how you can handle the fluid system. The Lagrangian analysis, proposed by Joseph Lagrange, is when you have a coordinate system which is attached to a particle. The coordinate system is all the time changing as the particle or the fluid moves through space. In contrast, an Eulerian analysis by Leonhard Euler is when the coordinate system is fixed in space and the fluid passes through it. So your coordinate space, being your control volume, being the black rectangle, is fixed, but the region of fluid deforms and moves away from it. Both of them are equally valid. The two of them are better for different purposes. And I included a slide here that gives you some idea of why one might be better than the other. The thing to point out that the vast majority of approaches use this, and this is what we're going to be using today and next week, and for the rest of this module. And the reason they do is because if you have a relatively simple body of fluid that is generally continuous throughout your control volume, then it's a lot more convenient to keep your control volume fixed. Okay, so we've got a few comparisons here. And I want you to think about what might be the advantages of one versus the other. And the first one, you've got flow through a pipe. The next one, you've got waves. And the next one, you've got topical analysis of a cough. And on the top row, you have an Eulerian analysis, and on the bottom row, you have particles. And the nice animation is from a free toolkit you can get from Google. So you can actually run something like this. So who wants to start off the discussion? Why might one choose an Eulerian analysis of a pipe? And why might one choose a Lagrangian analysis? What are the advantages that you get? Yep. Okay. So let's take those 2 points one at a time. So the observation was Eulerian might be used to simplify the flow, I think. Is that what you said? And that it might be less intensive on compute hardware. Or did you mean that for Lagrangian? Right. Right, okay. So Eulerian less intensive. In fact, both can be less intense. Both can be refined or coarsened according to the intensity that you need, right? So you can have many more squares in the Eulerian, or you can have many more particles in the Lagrangian. But the second point you make is a very astute one, because when you do the Lagrangian analysis of particles, it can indeed be extremely inexpensive calculation, because the way that the particle analysis works, you have to have knowledge of not just the particle that you're looking at, but the relative position of that particle to every single other particle in order to understand how they interact. And that becomes a very expensive and complicated process that, for reasons that we won't go into here, for computational reasons, starts to dominate the cost of your analysis. Okay, any other thoughts about why you might use one over the other? What about what they're modeling? Yeah. Okay. So the observation was that is Eulerian better for flow through enclosed spaces, and the other way around. So Lagrangian better for flow through in confined flows, like through pipes and channels, and Eulerian for flow around bodies, I think. So you're onto something. Eulerian is the most common method. So Eulerian, one way or another, has been made to work for most things. But where Lagrangian really stands out is when you have two phases or gaps between pockets of fluid. And I think that's what you're referring to when it hits an object, because you see this splash. You see this slosh and spray effect, which is incredibly difficult to capture using a fixed control volume. You need to use very, very small squares if you want to do that. So by instead choosing particles, even if they're relatively large, even if they're much larger than actually the droplet of the fluid, you can get this very complicated nonlinear splashing effect. And you see this in the bottom left. You see particles being convected in a flow that it would be just very difficult to capture otherwise. This sloshing and splashing, it's just hard to resolve that using the Eulerian approach. And this person coughing in an aircraft, you would probably, the top picture gives you a very good understanding of the average of the cough, but it doesn't give you the extremes very accurately. It doesn't capture the odd particle that goes all the way up and all the way down. Any other thoughts? Yep. Right, so yes, the observation was that the Lagrangian approach allows you to see probably understand better the dynamics of the problem, whereas the Eulerian one allows you to see the field much more, and that's very true. That's very true. Lagrangian, by definition, is dynamic because you're changing your control, your system to follow the particle, while Eulerian is mapping out the entire domain of your system. Okay. Good. No, I think that's very useful. I mean, so two things to take from here. There's more than one way to set up a control volume in a coordinate system. Next semester, in your mechanics module, you're going to be looking at coordinate systems for dynamic problems. You're going to be looking at Cartesian coordinate systems, which we use in Eulerian analysis, and you're going to be looking at intrinsic coordinate systems, which we use in Lagrangian analysis, which is where your coordinate system follows an object and changes as you go. Very useful for aircraft, for instance. And the other thing is that when you come back to CFD and modeling simulation in later years, you already have seen some of these things, which is, I think, pretty useful. Okay, So let's take a closer look at control volumes. What do we actually need to know about control volumes? Well, like we said at the beginning, a control volume defines something that you're going to look at versus something that you're not going to look at. And a very important step in continuum analysis was introduced by Reynolds, again of Manchester. His transport theorem, when applied to a control volume, allows you to go from the words to something mathematical that you can solve. But let's start with the words. It applies to any quantity that you're interested in. And at the moment, we just use a dummy variable, like, it doesn't matter what it is, it's B. And B can be mass or momentum or energy, or it could be temperature or pressure or concentration or turbulence. It's a quantity that moves in and out of that space. And there's basically a set number of questions that we need to answer in order to understand the full system. And these are written along the bottom. If we want to understand exactly the dynamics of that quantity in the system, we need to know how much that quantity is changing inside. So the total rate of change of the quantity inside the volume relates to three things. I probably should have put this one the same color as this one. And this is the basis for the analysis that we're going to be looking at. First is, if only considering the flow that stays there, that remains in the control volume both at the beginning and at the end, does something happen to it? Is something happening within the control volume that changes the pressure or the temperature? Is there a heat source? Is there a velocity source, a momentum source? Usually there isn't, because we have chosen our control volume in such a way that it's capturing a region of the flow that isn't changing, and we're only interested on the changes that happen at the boundaries. But sometimes there is. If you have a very large control volume, like the one that had the whole jet engine in, then yes, there's going to be changes in pressure, changes in mass inside that control volume. But the key questions are the ones in blue and green. How much is leaving and how much is going in? And if we want to have our proper accounting, our bookkeeping for the control volume, then we need to be able to understand this. We need to be able to answer this question. How much do we gain and how much do we lose? Not necessarily always per time, but in the steady state situation. And if we're going to understand ask the question in the context of a steady state question, so imagine a jet engine at cruise, then we need to introduce variables that are already taking into account the change in time. So like the mass flow rate, the volume flow rate, which is what we're going to be looking at next. So the three key questions that we need to understand if we're going to understand exactly how a quantity is changing is, does it change in the space that it's already in? How much is leaving and how much is entering? And if we can answer them, then we have a full and absolutely, well, entirely representative summary of what's going on. Here we go then. Here's a little bit more discussion. So this is, if you like, a summary of what we've covered so far today. We've got these three different methods: integral methods, differential methods, experimental methods. Which is the most accurate? Which is the fastest? How do we decide the control volume? As an engineer, where do we put our control volume? And, you know, any thoughts on which are you most likely to use in the real world? And on the right-hand side, I've put a series of zooms indicated by their color that show increasing scale and detail. So you've got a surface of a represented roughness of a turbine, and then the red region is represented maybe by the rear surface, the top surface of a turbine blade, and then the yellow represents actually that, you know, there's actually a lot of blades in the compressor that you need to calculate, and the green shows that actually the compressor is just one stage of the jet engine, and the blue finally is saying that the jet engine, or in the turbine in this case, maybe is just one part of the whole energy generation system. So you can appreciate that if our aim is to have a digital representation of the whole system, there's an awful lot of detail there. Okay, so what are your thoughts then? What if we are asked to represent the total output of an energy generation system, which approaches should we use? Integral, differential, experimental? Where do we start? Yeah, you have a question? You have a comment? Okay, so we take one small area and we expand. So similar to the graphics are showing, maybe, which way around, where would you start then? Okay. Okay, so I think, if I understand correctly, you're saying that it's good to start with the detail, but once we understand this one, we can use the answer from that to apply to the whole surface without having to do this everywhere. Yeah, very good, very good. So what you're describing is a very common technique in engineering at the moment called multi-scale analysis, where you limit looking at the smallest scales to probably the most important areas, and then you use the results from there to inform or train, if you're using machine learning, the regions that are similar, and then you iterate like that. What else? Any other thoughts? Your mission, you've just been employed by an energy company, and your mission is to design a digital representation of the energy generation system. What do you do first? Yeah, very good, very good. So the proposal was to start with a control volume approach, something fast, something that gives you order of magnitude analysis, then maybe look into more detail using some CFD, a differential method. And what about this experiment? And anyone think where the experiment might come in? Yeah? Yeah, yeah. So there's the old adage in fluid dynamics that when someone does an experiment of a flow, everybody believes the results except for the person who did the experiment, who knows how difficult it was to do that experiment. But when you do a CFD analysis of the same flow, nobody believes it except for the guy that did the CFD or the person that did the CFD. And this is representative of some of the kind of dilemmas and the trade-off that you have to make in this analysis. CFD is maybe fast but misses real-world information because it's an approximation. An experiment is, in theory, the perfect representation of what's going on, but it's expensive and it's full of errors, full of like human errors, user errors, things that you can't control. So it's very difficult for to repeat an experiment sometimes. So you use the two together. You use the experiment to get you your scale. It was a very good point about the scale analysis. You use your Reynolds number to reproduce the same conditions in the experiment that you expect to have in reality, and then you do a CFD maybe to compare to the experiment to get confidence in the CFD, and then you can look at it in more detail. And then taking the very first comment, you apply them at different scales, and you can build it together to get a full representation. Anybody heard of the digital twin idea? Digital twin? Hands up, anyone? Okay, amazing. Digital twin, by the end, this is one of the buzzwords in engineering at the moment. I'm convinced that those of you that stay in engineering, maybe a third of you will have a job title that says digital twin something by the end of it. I think it's going to be in everything. Digital twin is, as you can imagine, a digital version of a system that you you have in some environment, a cloud, or something that you've trained, maybe using experimental data, machine learning, models, and that if you experience a fault in a real system, you can reproduce that fault in the digital twin. You can analyze where it might have come from. You can propose fixes and modifications, and you can do all that very quickly because it's in the virtual world without having to do any downtime, stop your energy generation equipment, make any difficult and potentially dangerous interventions or observations of the system. One of the key areas that we envisage using digital twinning for are potentially the most dangerous areas of engineering: nuclear engineering or fusion, where and fusion energy as well, where you have such high pressures and temperatures and dangerous environments that you can't physically access or interrogate the system. You need to model it. So digital twinning, remember I said that. I'm sure you'll be very familiar with it by the end of your degree. Okay. So we've introduced integral analysis, differential analysis. And we said at the beginning that the whole purpose of a control volume is to apply rules that we can use to understand the physics of what's going on. And this is what we have here. We have the three pillars of fluid mechanics, the three pillars of maybe continuum mechanics in general. The reason there are four that are then joined to be three is that in textbooks at the beginning, because we do 1D analysis or 2D analysis, we usually look at the separation between linear and angular momentum. But later on, and in general terms, throughout, basically always, you can't really separate linear and angular momentum. If you track the momentum of a system, then you might be moving in one direction relative to another axis. So relative to one axis, you might be rotating, whereas relative to another, you might be moving in a linear way. So they are essentially the same thing in 3D space, but can be considered separately when you're looking at 1 or 2D space. Conservation of mass, conservation of momentum, conservation of energy. I said it before, Newton's second law, F equals to ma, which you can also write as m times dv dt, A, is essentially the change of momentum, the d by dt of mv, which is momentum. Newton's second law is the conservation of momentum. And we use that all the way through mechanics, all the way through continuum mechanics, to understand and analyze the forces that are acting on a system and how they lead to a dynamic change. And this, I put this in for fun because this is from my 4th year module on computational fluid dynamics. And this is a map, if you like, of all of the different approximations that you can use in fluid dynamics for various different systems, whether it's supersonic flow, low-speed aerodynamic flow, automotive incompressible flow, microfluidics, continuum, maybe Knudsen number, rarefied gas flow, turbulent flow, laminar flow, transitional flow. All of the types of flow that you can have effectively can be, there is an approximation that is suitable to them that's found in this diagram. And it's only a small version of the full diagram. There's many, many more methods that have been proposed for various fluid mechanics problems than this. So why do I put it here? Well, the main reason is to link between what we're going to be doing in this module and what you're going to be doing in the future years. At the moment, we're about to describe the full Navier-Stokes equations. We're about to define the entire system of continuum mechanics that you need to describe anything. Any matter, which is either a solid or a fluid, but principally a fluid, can be described entirely by those equations. But they're complicated and they're 3D and there's lots going on, so you generally start down here. And as you go through the years, you build up the blue column and you get to the top, and then you can use the most advanced techniques to solve the problems. But it's still important to know where you are on the map. So we're building up to use Bernoulli analysis, 1D analysis, where we're generally assuming that there isn't viscosity at the walls, like we said at the beginning of this course. We assume that there's no viscosity, so we can treat the flow as a 1D most of the time when we're looking at complex systems. And Bernoulli, as you will see in the future, is only valid along a streamline. So it's only valid in regions of the flow which are very far away from a wall. Okay. So, I mean, hands up any of you that have used Bernoulli already, Bernoulli's equations, in your previous work, in modules, or already this. So we've got a couple of hands, Was that in physics? Yeah. Have any of you used Euler's equations? Yeah? Yeah? Was that maths? Sometimes it's looking at characteristics or wave equation. In mathematics, in mechanics, you sometimes look at the wave equation to model how the waves transition through a fluid. Hands up if you've applied the conservation of mass. Right, that must be everybody. And the conservation of energy? Everybody, right. So these are absolutely the fundamental things, the cornerstones of physics. And all we're doing here is translating them into a control volume. We translate them into a control volume, we get the absolute system of equations, which is the Navier-Stokes, and then we simplify. Okay. Any questions? Comments? No? Good. I think we're going to leave the rest of this and the subsequent parts till next week. I think the comment was made earlier that these notes weren't up very far in advance. Please try and have a look at them before Monday, the rest of them and the rest that I'm going to put up over the weekend. And the last thing is a reminder for two things that you've got coming up. This afternoon you've got the coursework, and tomorrow you've got the tutorial. Okay, that's it. Thanks. Have a good weekend. I'll see you next week. Yeah, come here.
We have another class, right?
Tutorial. Sorry?
What do we do in tutorial?